Hi everyone. I'm happy that I can that the issue is solved, and thanks for having me. Sorry that I'm not there in person. I'm teaching. So I'm going to give a very brief overview of about like 15 minutes of some of the works that we have been doing in my lab, and our focus is on multimodal modeling, but a specific form of it that I will define shortly. So just to establish the picture, and what I mean by multimodality is that broadly as a concept, there's a physical world out there, and we use various sensors and representation. If you take a picture of this physical world, it becomes an RGB image. If you take a picture with a depth camera, it becomes a depth. If you represent that depth with another like representation, like surface normals, becomes another representation, another so-called modality of information there. We can ask someone to put a bounding box around it, becomes object detection, or segment it out, or describe it with text, becomes language, even latent representation. So this would be like a clip features of this observation from the physical world is a specific representation. So these are all various modalities of information, various representations of one underlying physical world, and what ties them together is the groundedness in that physical world. And in general, often we deal with one or a subset, a small subset of these modalities. For example, in language modeling, there's obviously the text, and vision language models is image and text. But broadly, the concept of modality is that there's one grounding physical world, and we are dealing with various projection of it. We call these projections modalities of information, basically representations, and so on. So we have been working on modeling not just one or two, but unified systems that can integrate and model a diverse set of modalities representing this world. And there are three characters that I want to highlight before I go through the talk. And I think it's useful to keep in mind is that in this definition, in this approach, multimodality is more than images and captions, images and text. There's like a diverse set of modalities, like I said, that can have benefits to us. Also, modality does not have to be tied necessarily into a sensor. So multimodality is a superset of multisensory. Not every one of these modalities that they deal with have to have a hardware-based sensor in order to be useful. So we'll see examples of that. And also, internal multimodal learning is more than fusing multiple modalities in order to have a complementary representation. It is not about LiDAR plus cameras or radar plus LiDAR because one of them works in fog and the other one doesn't work in low light to cover each other's blind spot. Multimodality can be more than a test time mechanism. It can be actually a self-supervision mechanism during training in order to learn a representation in the first place. So I'll talk about that hopefully towards the end of the talk if you have time today. So these are three characters that runs through the research that we do. I wanted to highlight them, and then I'll now talk about models. So this is what I showed as a diverse representation of the world, and one core function in general that we are looking for in multimodality to enable these various stories that we talked about is the elementary capability of predicting any of these modalities from any other. And the so-called any-to-any multimodal modeling. And that's what I'm going to primarily focus on today and the methods that we have developed around it. So one example of it that is now a couple of years old is 4M, is multimodal mask modeling. What 4M basically does is that it has this diverse set of around 21 different modalities that we have created in a data set through pseudo-labeling, through data collection and various things. So it's worth looking at it. What they are is like, there's RGB images. I'm not sure if you can see my cursor. I hope you can, but if not, I'll verbalize it too. So there's images in there. There's geometric modalities like surface normals and depth, and semantic ones, objects, bounding boxes, latent neural network features like Dino, Clip, and local and global ones, obviously text, metadata expressed in the form of text, sketching, and so on. So now this is, we view it as more like a prototyping dictionary that allows us to advance on the type of models that would be able to connect diverse set of modalities. So the way that 4M does, it's basically encoder-decoder VIT architecture. Like I said, this is a couple of years, like it was developed a couple of years back. Now we have moved towards decoder-only architectures, but still encoder-decoders have actually a place. They have advantages, even with the performant decoder-only models today. But 4M was an encoder-decoder, VIT. It's pretty standard and homogeneous architecture. All these modalities are tokenized, and the way it works is that you randomly sample a subset of these input modalities in any possible subset. So you could sample some of the RGB image, some of the depth, and then predict another random subset. Like say some of the segmentation and some of the text out of it. So any of these possible subsampling subsets is randomized, and it comes up during training. And there is a slew of like efficiency mechanisms and so on to make this scalable to multi-billion parameters. And so that was basically 4M. I'll just show you brief results of it, but I'm happy if someone wants to talk more details about the technical under the hood in the Q&A. So what you can get after you train it, you basically get at least like a multi-task model, meaning that you can give it an image and can predict all of these other modalities out of the box. It worked reasonably well. I can say that from a background in multitask learning, that up until about 3-ish, 4-ish years ago, it was never possible to have one multitask vision model that doesn't come with a tax. So basically, they would always underperform task-specific models. But now we seem to have got to a point where there's not much tax for multitask learning, meaning that if you have n single task networks, you can pack them in one big network if you do the recipe well, and you will not really lose performance that much. And these predictions that you see are at the level of the ground truth and the level of single task models that this was pseudo-labeled on. Okay, so I mentioned it's any to any. So what I showed in the previous slide was, one to many, but it should be really, if it's any to any, it should be a full matrix basically, right? So this is that full matrix where each row, the first column, shows the inputs, and the other columns is the predictions of the rest of the modalities out of that. So you can see that this is really like any to any, and all of them work comparably well, except for the ill-postness of some of them. Of course, some of them are ill-post, right? You can go from RGB image to depth, but you cannot go from text to the depth of the original image. But it's a generative modeling, so it generates a depth that conforms to the text prompt, but it's not obviously the original depth. So basically, it does what is expected it to do, and it works reasonably well. And so these were the set of modalities. What's obvious here is that it's diverse, but it is not complete. So there's a lot more in the world that we care about. So we added to this, again, prototyping dictionary, a set of modalities that are worth modeling and developing architectures around, obviously like motion, like time series, multi-frameness, like explicit 3D rather than like 2.5D, and IMU, low dimensional, and so on. So one extension is going to 3D. Like I said, like 4M originally had geometry-based or modalities like depth and so on, but they're so-called 2.5D. They're not in full 3D, right? They're like a motion plus image plus parallax. So we were curious about extending this to 3D, and interestingly, actually, the same recipe works. It's a matter of tokenizing your 3D modalities, which is quite non-trivial. Much of this project has gone into being able to tokenize like various modalities like Gaussian splats and nerves and meshes and so on. But once you can do that, it actually works reasonably well. The same exact kind of any-to-any architecture that we developed for images transferred here. These are actual results of it. You can obviously get 3D generations out of an image. In fact, actually, the model, you can think of it as it doesn't even know which modality it's dealing with. There's a bunch of tokens for it. But once you audit it afterwards, it actually works quite well. So here is an RGB image to these 3D. From the perspective of the model, is really just mapping an RGB image to another, you can think of it to another image modality, because it doesn't seem to be any bias towards, say, image to image works better versus image to 3D doesn't work. The same question applies to videos as well. Like, what about videos? The same recipe, we have been able to extend it. So here we turn the video into, instead of only RGB representation of it, into representation in terms of depth and normals and so on, and applying the same recipe to it, turning an any-to-any, developing an any-to-any video model. It does work with very similar behavior. So you can give it an image, you can give it a video, RGB video. It can predict all of these other representations of the video, depth and optical flow and bounding boxes and transcriptions with timestamps and so on out of it. And you can make it, again, the full matrix. So you can give it depth or normals or bounding boxes and get the other things out of it. I think videos have an interesting implication here, these multimodal videos, because I'm sure many of you are aware of this discourse in the community on like the world modeling, and then there's a debate, okay, what makes a model world modeling? Is a video generative model a world model? Is it not? Of course, there's a lot of opinions and feelings about it, but one character of the discussion is that, okay, many would do video modeling in the RGB, in the original sensory domain, and some believe doing it in an alternative, like say Latin representation or something else. So I think that's a valid actually question point. But what I'm saying here is that if we have actually a multimodal model that can traverse across different modalities, the question is not really like that applicable anymore. So for example, you can, let's say, ask, should it predict in the pixelless space or in abstract spaces? This is the reformation of the word modeling question that I had. So for the task of going from text to video, like this is video generation, you could train a model to generate RGB videos for you. But if you have a multimodal model, you can what it does, what would a caption to video model do? It would have to solve two tasks simultaneously. One thing, it would have to model the future semantically, like what objects are in this scene and how they should move, perhaps, and so on. And the other thing that it has to do is that it has to model low-level pixel details like lighting and texture and all those, and fine-grained interactions. And it has to do it really simultaneously without any structure. But if you really approach video modeling as a multimodal modeling, you can think of it as you can construct a sequence, a chain of modalities, a chain of thoughts, if you will, across different modalities in order to go from caption to RGB video in the end, but you're hopping over middle modalities that are more abstract. It could be latent, but it's still more abstract than RGB. So in this case, for example, if you go to transcript and cyclip and detection and so on, you'll end up with a different RGB video, a better quality RGB video, quantitatively speaking, than if you use the same exact models, but you do a direct prediction. So I have some quantitative analysis here. It seems a pretty stable observation, but I'm not showing it in the talk today, but I'm happy to talk about it if others are interested in. So what I would like to also emphasize is that everything that we do, it is more like a prototyping in order to find the right model architecture that would broadly apply, and not just for content creation, for creating nice looking images and videos, but ultimately be a way of doing data-driven modeling on a domain that we don't have a model for. So this is more like in the, let's say, in science, in astronomy and neuroscience and so on. We don't really have a model of an underlying problem that we're dealing with, but we have multimodal data around it. So if you really have competent and models, data-driven models of the underlying problem, we could do things, scientifically speaking, with that a model enables. And of course, this model should be a very good approximation of the underlying problem that they're dealing with, which is the challenge of these models, but that is generally the idea. So ultimately what we want to do is we don't want to release the final artifact. We want to release the architecture, open source code, and so on, that domain experts can apply it to their problems. And this has happened to a good extent, luckily, with 4M. Like, we released the code base, and people, for example, this ION astronomy model, they used their radio telescope data, but the same exact architecture that we have, they basically swapped out images and depth and so on, and just swapped in like hyperspectral data and whatever they had and they created a predictive model of an astronomy domain that, from what I understand, actually works quite well. And similar story for like Earth observation and biology and so on. So this is kind of the ideal scenario for us. We don't want to compete with Gemini and ChatGPT. We want to release the general framework that domain experts can apply to their problems. One other topic that we are quite interested in and is going to be blended with multimodality is variable length representation or variable length tokenization. So I'm sure you're all familiar with tokenization, why we use it. One strong property of it, well, one obvious property of it today is that it's relatively fixed length. It's relatively independent of the image or whatever data, the complexity of the underlying data. So if you get a simple image, it gives you a fixed set of tokens. If you give it a complicated image, a lot of content, same. And this has like consequences, and it's clearly not necessary to. So Picasso Latour like depicted this concept very well, that you can show the same semantic thing, but very few strokes at the bottom right, or a lot of strokes on the top left. But something is preserved, but something is also lost. So can we bring this concept to tokenization, which would make things easier in terms of efficiency? Like if you can get far by predicting a few tokens versus 256 tokens, of course, you will get a massive efficiency gain there. And similarly for representation learning. So there's a lot of work in our lab on so-called FlexTok. This is flexible tokenization. This is the image version of it. I'll show you the result. So this is let's say the image that we are tokenizing it. If you tokenize it with the full length of the token length expressiveness, 256, you will get, this is the reconstruction, is quite close, right, as you would expect. But what if you actually use fewer and fewer tokens? So 256 is the full sequence, but what does the first token and second token and fourth token and eighth token in that sequence looks like? So if you decode it, you can see that early on, it preserves a notion of semantics. And this is trained without any language, right? So there's no bias from semantics is coming in. The way it works is that it's a combination of a nested dropout in the bottleneck plus self-supervised losses of like Dino and so on. Again, Dino is important to be there, but again, Dino was not trained with language, right? It was self-supervised. So it is interesting that we are getting emergent semantic structures without bringing language in by marrying compression into with things like Dino. So, and like I said, this is useful, especially for compression and efficiency. Say if you want to like do text to image. So if your prompt and image are going to be simple, then with very few tokens, you will be able to satisfy your downstream evaluation very well. And if it's more complicated, you can see an example. The top row is simple, the bottom row is more complicated, and that comes out in the evaluations too. So for more complicated things, you need to generate more pixels, for more tokens, for less complicated, less, and you can truncate it at any point that you want. We have extended this concept to videos too. We haven't released it yet, but it'll be soon. So the videos actually make it, in my opinion, a lot more interesting because now we have two axes. There's conditioning across time and a conditioning like within the image. And it's very interesting to see what emerges when you compress like videos in this framework. And you can see that often motion is preserved, like the camera motion is preserved from the original video, but then semantic concepts are replaced. There's one human and there's another human, but then what is interesting, I think I want to point out to appreciate that this is like a 1 token, 2 token, 4 token representation. These are discrete tokens. So this is basically a 2-byte representation of a video. So out of a 2-byte representation of original video, this is what is coming out, which is, of course, it's only 2 bytes, right? So it has to be very, very compressive and lossy, but what is preserved is still like surprisingly close to the original in the semantic form. Okay, so that's video FlexTalk. Oops. And So I will finish now, but I want to raise a few things is that like this sort of ordered token representations gives rise to interesting question in terms of test time, compute, and search. So my student Zitong, she presented a poster during the ELLIOT meeting the past 2 days, and she's there. I let you speak with her. The website is very interesting. It has a lot of hands-on way of gaining an understanding in this problem. So you're welcome to visit it or catch Zitong and have a discussion with her. Ozar also, who did the video, is there. Like I mentioned, also we have now moved on to exploring with encoder-decoder, with decoder-only architectures. Many of the things that I showed so far with encoder-decoder, but it's very interesting to bring decoder-only in and get efficiency out of it, like KV caching. This is basically getting inspired by advances in language modeling and see how we can bring them to multimodal data. So that's an active line of research that we'll do, and we have some releases coming up. And there's this thing that I also mentioned earlier. Sorry, I went too fast. That multimodality as supervision. We have a study paper on this topic, and that is coming up in ICLR, so you're welcome to take a look at it. But it really goes down to saying that, okay, can we not start with any supervision except for the multimodality itself? Like you're a robot and you have multiple sensors, and you don't know anything about the world, but you're seeing, you're hearing, you're touching, and those things at the same time. Can you learn a good representation by virtue of just cross-modal learning? And this also makes it interesting because I think it brings this angle of a specialization in that questions how much data actually we need in order to have good foundation models. So the common assumption that you have a lot of data, you have to be like at the internet scale to be competent, but it doesn't seem to be necessarily actually true, especially for many of the real world applications. So we try to address it in this paper. We will release it in a little over a week, so you can tune into that. And there's also an app there if you deal with hardware and physical domains. There's an app for iOS devices where you can simultaneously record all of the sensors of your iPhone and iPad, being whatever, like LiDAR and accelerometer and magnetometer and barometer depth, RGB, all those stuff. So you're welcome to use it. It's open source fully. Okay. So I think I'm going to finish. I talked about core architectures of multimodal learning, especially the class of any to any models, how to handle diverse modalities like time series data, 3D, well-structured tokens seem very interesting. We are actively working on it. Efficiency, specialization, and test time compute, and ultimately, I hope that we can continue to open source and support both like scientific models and as well as like application domain models that people care about. Thank you so much.